posted on the Qiskit YouTube channel. And I'm very happy to see so many of you tuned in, including our first time having 3 visitors to the seminar at once. So it is really my pleasure to welcome Doctors Laura Cardani, Johan Pop, and Francesco Valenti, who will be presenting on their great results that just came out 2 days ago on the archive, Reducing the Impact of Radioactivity on Quantum Circuits in Deep Underground Facilities. So hi, everyone. How are you doing?
Hey, Zlatko. Thank you for organizing this. Great to be here. Hello, everyone.
Johan, it's great to see you.
Yeah, thank you for the invitation. We are very excited to be here. Hi.
Hi, Laura. And hello, Francesco.
Hello to you too. It's a pleasure to be here, and I'm very excited to give this talk. Thank you for this opportunity.
And where are you guys tuning in from? Just give us an idea.
I am tuned in from Karlsruhe Institute of Technology in Germany, where I'm currently doing my PhD.
And I think Laura is in Rome, and Johan is, I think, in Germany as well. Yeah. Johan is a researcher in quantum circuits and ultra-sensitive detection, charge carriers, topological materials, and the list goes on. Johan got his bachelor in Transylvania, followed by a PhD in Grenoble, spent 4 years as a postdoc in the group of Michel Devereux at Yale, where I was a young student at the time under his training and supervision. So I learned a great deal from Johan, for which I remain very grateful. Since 2015...
That's very kind, Zlatko. That's very kind. Thank you.
Thank you, Johan. Since 2015, Johan is a group leader in Karlsruhe Institute of Technology in Germany, and supported by the Humboldt Foundation and Helmholtz Association, and I think a number of other associations that you can read about on his site. Laura Cardani was a Dickey Fellow at Princeton. In 2017, she became a permanent researcher at INFN. She spent most of her career in the development of detectors with ultra-low radioactivity levels to search for rare particle physics processes, which you can see how that meshes in today with what we have. Since 2018, she's the PI of the METRA project for superconducting circuits in low radioactivity environments. And our speaker today, Francesco, who's based in Germany now, is from the Italian Alps. He's doing his PhD in the group of Johan Pop and Oliver Zander, and he's been working on FPGAs and quasiparticles, as we'll hear about today. And Francesco, you can pull up your slides, and meanwhile, tell folks that the format is interactive, so ask questions during the talk in the comment sidebar, and we'll try to get to those. And I'm sorry, Francesco, but I'll probably interrupt you very often with questions. So I think it's time we get started. Thank you.
Thank you for this introduction. My name is Francesco Valenti. I am a PhD student in Karlsruhe Institute of Technology in Karlsruhe, Germany. And today I'm going to talk about reducing the impact of radioactivity in superconducting circuits with the help of Laura Cardani from INFN in Italy, the National Institute of Nuclear Physics, an expert in radioactivity. I can summarize the impact of radioactivity in superconducting circuits with this drawing. Radiation can hit a superconducting circuit, and if the energy is strong enough, can break a Cooper pair in the circuit. Or it can hit the substrate onto which the circuit is deposited, generate phonons there. These phonons can travel through the substrate, reach the circuits, and break a Cooper pair there. So the impact of radioactivity in superconducting circuits is breaking Cooper pairs, or alternatively, generating quasiparticles. This amounts to destroying superconductivity in a way. Thus, this is a negative effect. This is a qualitative look. Can we have a quantitative look on this? And the answer is yes. One thing I would like to note is that the substrate has a volume that is much bigger than the circuit, and thus will act as a predominant absorber for the radiation. As I was mentioning, can we have a quantitative look on this effect? And the answer is yes. This was the subject of a recent preprint from Vepsalainen and co-worker from the Will Oliver group in MIT, where they quantified the impact on a superconducting qubit. What I show in this plot, it's the relaxation rate of a superconducting qubit, thus the degradation of a superconducting qubit, as a function of radiation power onto this qubit. So really, degradation as a function of radiation. And especially in the high power regime, we can appreciate that the more radiation, the more qubit degradation. If I want to have a good qubit, then what I want to do is reduce radiation and go down along the dashed lines. I will not be able to do that presently because we will reach a floor that is given by sources of relaxation that are not related to quasiparticles generated by radioactivity. We can then make a thought experiment. What happens if we get rid of these other losses? Will we be able to reach this regime down here following the dashed lines? The floor from environmental radioactivity will then block us. And for a transmon qubit, the floor will be at 1/4 millisecond, as it was shown in this recent preprint. And state-of-the-art transmon qubits have a coherence that is 10 times smaller than this. Thus, we will only need to improve the coherence of transmon qubits that is due to other losses that are not related to quasiparticles to reach a regime in which radioactivity will start to limit the coherence of qubits. And this is for transmon qubits, the type of qubits that are shown in this work from the MIT group. Other types of qubits are already limited by quasiparticles, qubits such as flux qubit or fluxonia. This is where I would like to make the switch from this quick review from the work of Vepsalainen and co-workers to our work. Because the question that is answered by the work of Vepsalainen and co-worker is, are quantum circuits sensitive to increased radioactivity? Because the way they sweep the radioactivity power on the x-axis that I've shown is by putting an external radioactive source. This is a destructive approach in a way. And in our work, and what I will talk about in the following slides, what I will try to answer is, can we stop environmental radioactivity from degrading a quantum circuit? And stay tuned for the answer. This is a good time to introduce our superconducting quantum circuits that I've shown here in this figure. Our circuit are strip-line resonators, A, B, C, deposited on a Sapphire chip, put on a waveguide, and excited to measure the reflection. We make them with high impedance, so these will factually be kinetic inductance detectors. How we use these kinetic inductance detectors as a probe for the effect of radioactivity, I can start to answer this question by talking about the material with which we make them. That is granular aluminum. Granular aluminum is a composite material made of superconducting aluminum beads in an aluminum oxide matrix. which is fabricated by depositing aluminum in an oxygen atmosphere. This is a material that has been known and studied for decades, but has recently attracted interest for the superconducting quantum circuit community, as is outlined in the work of Maleva and co-workers. This is because for a given common geometry choice that is very thin and long circuits, this microstructure of superconducting islands separated by oxide can be interpreted and modeled as a chain of Josephson junctions. Thus, if we are able to change the oxide thickness between grains, we can change the coupling of this Josephson junction chain. I show here on the x-axis the oxygen flow that is at operated depositing granular aluminum, and we see that this relates to a tunable normal state resistivity, which is then relied to the kinetic inductance when in the superconducting state. And the kinetic inductance is a tool that will allow granular aluminum to be used as a probe for radioactivity. And this is how. As I mentioned before, yes?
Question before we get a little too far. Do we have sorry, I guess a few slides ago you had the resonators, which are just strips of metal on a substrate, right?
Yes.
Some of them are thin, some of them are thick, and the lengths are different. Can you talk a little bit about the design choice? I mean, I guess you're adjusting the frequencies to be different, so you can do some multiplexing later. But can you speak a little bit as to why the thicknesses are different and not just the length?
The thickness is the same. We changed the length and the width in such a way to have, as you mentioned, frequencies within our range and different coupling to the waveguide mode that will allow us to distinguish between them.
Right. Yes. Thank you. Sorry, I should have said width, not thickness is 20 nanometers. The width you're varying as well to adjust both coupling and frequency independently. Got you.
Yes. As I mentioned previously, radiation will affect our circuits by breaking Cooper pairs in them. And this is mediated by phonon transmission in the substrate. What happens is that once phonons generated in the substrate reach the superconducting circuit, if their energy is sufficient, they will break Cooper pairs, decrease the Cooper pair density, and increase the kinetic inductance. And this will manifest itself as a drop in the resonant frequency of the superconducting resonator because of the increased kinetic inductance. We see here the shift from the unperturbed resonant frequency of a resonator over time. Once phonons hit the resonator and break many Cooper pairs in there, what I call a quasiparticle burst, then the frequency will drop and will then relax to the unperturbed values while quasiparticles recombine into Cooper pairs. And the burst will create a drop in frequency that is bigger as the kinetic inductance is bigger. So a high kinetic inductance material, or a material that can be made to have a high kinetic inductance, such as granular aluminum, will be a good choice to be a probe for the effect of radioactivity. Since these bursts are mediated by phonon that propagate in the substrate, then if I show my 3 resonator here sitting on the sapphire chip, then phonons will reach resonators at the same time or very close in time, and this will be a source of time-correlated quasiparticle bursts, then time-correlated drops in resonant frequency in these resonators. What I show here are the phase response of the resonant frequency point or better yet, the offset from this point for resonator A and resonator C over time. And we do observe the drops that I mentioned. And when these two drops appear at the same time in the two resonators, the drops are connected with dotted lines. Note that, for clarity, the y-axis referring to resonator C is inverted. We see that the majority of these bursts are indeed correlated.
And Francesco, do we have any idea how quickly a phonon from one end of the chip would propagate to the other end of the chip?
To my knowledge, the speed of sound in Sapphire is of the order of 10 kilometers per second. Thus, 10 millimeter per... Sorry, I'm not very good at calculating with my head, but we can calculate it.
That's fine. It sounds like it's pretty fast.
It is in principle.
Faster than timescale. It's interesting to see. Yes, I think Joey Subtle is tuning in. He says tens of nanoseconds, so it would be much faster than all the time scales that we're looking at here in the experiment. So you can kind of assume that everything is that all the phonons have propagated, right? You don't need to worry so much about their temporal dynamics. Although there's a question if that's the same speed of sound at cryogenic temperatures.
This is a good point, and we can just assume that it is, but I cannot motivate this. The source where I remember reading that the speed of sound is 10 kilometers per second was not dealing with cryogenic temperatures. So it very well may change. This is a good point.
Although it sounds like it's probably safe to assume that the dynamics are faster than what we're going to be concerned with here.
Yes. For our intents and purposes, we can consider the burst appearing at the same time. At least for our readout scheme with which we can look at two resonators at a time, what we see, it's always in the same time slice.
And this is really, oh, sorry, you on?
Yeah, I just I wanted to add very quickly that this speed of sound was measured actually in some experiments in the Alessandro Monfardini group in Grenoble and also in Jonas Muidzina's group in Caltech. So if I remember correctly, I think it's 3 kilometers per second, something like that. And it allowed them to actually triangulate the position where these phonons are coming from. So that's the principle. So you can definitely distinguish the arrival time.
Okay, nice. Okay, so it's kind of at the nanosecond level, but it's distinguishable.
I think it's longer, actually. I think it's more like a fraction of microsecond.
Oh no, this is good. Very cool, and it's very interesting. You know, I mean, the resonators, they have a pretty significant line shift, right? Like hundreds of kilohertz. By the way, what are the quality factors or sort of the line widths of these resonators?
The line widths are, let me think about it. For resonators A and C, the quality factor loaded is 10 to the power 4. So the line width would be of the order of some kilohertz. So these drops are of the order of the line width.
Okay. Great. Yeah, so you have great sensitivity. And can you help us understand a little bit better? Thank you for taking all the questions, by the way. Can you help us understand a bit better, as opposed to normal transmon qubits or other qubits, why there's so much more sensitivity here with the granular aluminum? I guess it has to do with the fact that you have all the kinetic inductance coming, or most of the inductance in the resonator mode coming from the kinetic inductance of the wire itself, which is very susceptible. I guess with normal qubits, you have the junction, which provides all the inductance, and it's it's microscopic, whereas here you have a large distinguished, large piece of metal. So is it that because it's smaller, the Josephson junction couples less to this background, and that's why we see potentially less shift there? And maybe I should let you answer.
I guess the sensitivity, your question is how can we be so sensitive to these bursts? Am I interpreting this correctly?
Yes, yeah, because you have a really nice sensitivity, of sort of hundreds of kilohertz shifts on these granular aluminum resonators.
Yes.
Just trying to understand versus a normal resonator, which might not have as much.
As you were hinting, you were absolutely correct when you said that this has to do with the kinetic inductance. The shift in resonant frequency will scale with the shift in quasiparticle density, so the amount of quasiparticles generated, times the kinetic inductance fraction, so the ratio between kinetic inductance and total inductance. And for these particular resonators, the kinetic inductance fraction is unity. We are dominated by kinetic inductance. This is what makes them so very sensitive to quasiparticle bursts.
Thank you.
And as I was showing in the plot on the right, what we see are time concomitant bursts observed in resonator B, shown on the left y-axis and as upward triangles, compared to those observed in resonator A on the x-axis. And the same for those observed in resonator C, compared to, again, resonator A. Resonator C are shown as downward triangles. All the colored points are points that at the same time exceeded 2 standard deviation of the unperturbed value in both resonators at the same time. They can have different magnitude, but they definitely show that they are happening. Something is happening at the same time in both resonators. This is a particularly bleak scenario for superconducting qubits, because having some error that appears in a time-correlated manner across different devices on the same substrate would make error correction more tricky.
And Francesco, I'm going to raise a question. This is not my question, but it's an interesting one. What do we know what the ratio of correlated to uncorrelated is? Like, are uncorrelated drops thought to be radiation absorbed in the superconductor, or some other effect?
This is a good question, and we are not fully equipped to give a robust quantitative answer to this, because what the data that I've shown here is, let's call it demonstrator data, that we measured with a time multiplexed readout that we sketched up. But in order to answer up properly how many bursts are correlated, we would have to take more data over a longer time and with more precision. The time resolution of our let's call it homemade time multiplex readout for correlated bursts had a time resolution that was about 0.3 seconds. So it was not very pinpoint. This is an interesting question, and we should answer it after taking more data with a better scheme.
No, that's really interesting. And I see your slides are generating a lot of questions already, so I apologize for interrupting you so much. I hope it's okay.
To finish the previous question, the important thing is that the question that I can give now, how many of these bursts are correlated, the answer is a good deal, apparently. And this is already interesting to us.
Mm. And I guess you do see broadening of the line widths with the bursts, right?
I will get to that in a minute.
Perfect.
Sorry, I interrupted you. Was there another question?
Oh, that was the second question from Amir.
Ah, okay. Then, yes, another tool or another property of granular aluminum that makes it useful to probe for the effect of radioactivity is dissipation. Because the internal quality factor of granular aluminum for the resonators that we made is dominated by quasiparticles. The dissipation is dominated by quasiparticles. And I will convince you of this by showing you that the dissipation is not dominated by the other usual suspect when it comes to superconducting losses, which is dielectric losses. What I show in the graph is the internal quality factor measured at single photon as a function of the participation ratio, which tells me how much of the energy of my electric field is wasted by polarizing the dielectric. And a material such as aluminum is predominantly dielectric limited when it comes to internal quality factor. So the good strategy in that case is to follow the x-axis, which shows reducing participation ratio, which will allow us to get very high internal quality factor. These aluminum resonators have almost 20 million internal quality factor. Then can we do the same thing with granular aluminum? Can we decrease participation ratio and get very high internal quality factors? When we start from very big participation ratio, we do see an improvement when we reduce the participation ratio, meaning that in that regime, granular aluminum, as shown by this point, is dielectric limited, and decreasing the participation ratio put the values on a slope, which also interestingly shows that it has this comparable tan delta of aluminum. But then when we get to a regime where the participation ratio is very small, and which would give us very good QI as for aluminum, we find that granular aluminum resonators saturate on a floor and give us order of magnitude smaller internal quality factor compared for similar geometry aluminum on the same substrate. And we attribute this to quasiparticle losses because the kinetic inductance fracture is about an order of magnitude higher than in aluminum, meaning that we will have an order of magnitude more quasiparticles, and this can explain well this excess loss that doesn't allow us to get the same internal quality factor of aluminum. Thus, we can look at internal quality factor of our resonators as another probe to check the quasiparticle density. Then, if quasiparticles is our window on the effect of radioactivity, then another step that we have to take is make sure that the quasiparticles that we see are only due to radioactivity and not from other sources. Let me then briefly go over some other quasiparticle sources. The more obvious one being radiation leaking from the wiring in my cryostat. We make the effort of cooling down our superconducting circuit, but then we have this coaxial cable that goes all the way to room temperature. We don't want heating coming down from this line, creating excess quasiparticles. And the solution is to filter and attenuate RF lines in cryostats, and we take care of this. Another source are infrared radiation coming from outside, as was first pointed out by Barents and co-workers. And this is instead fought by multi-stage shielding and by using absorbing coating for the shielding. And also, we take care of that. And another possible sources is a strong readout drive, the tone with which I excite the resonator itself, as was pointed out by De Visser and co-workers, which is relevant for the detector community, but not relevant for the superconducting qubit community, because the readout power is of the order of 1 photon circulating in the resonator, which is not enough to break Cooper pairs. The two quasi-particle sources that we want to deal with then are phonons in the substrate that can or cannot be generated by radioactivity, as was first pointed out by Svensson and co-workers, and radioactivity itself. And to get rid of them and to better our superconducting circuits, respectively, we can implement phonon trapping and radiation shielding. And this will be the subject of the rest of my talk. How do we achieve phonon trapping? What is a phonon trap? If I have a superconducting circuit, what I call a phonon trap is a neighboring superconducting island with a lower gap. When I say neighboring, I mean this superconducting island is close to the circuit on the same substrate, but not in galvanic contact to it. And this is where granular aluminum again becomes a very good choice, because the critical temperature of granular aluminum, the gap of granular aluminum, can be tuned with its resistivity. And as I shown before, we can easily tune the resistivity by tuning the oxygen pressure during deposition. The critical temperature will follow a dome-shaped behavior as a function of the resistivity, and it will always be above the one of pure thin-film aluminum. If I make my circuits with granular aluminum, then I can use aluminum as my trap, as my phonon trap, since it has always lower gap. And then this is what happens. This is a story of what happens in the circuit trap system at the relevant energy scales that are the gap of the circuit and the trap over time. First, something can generate phonons in the substrate, as indicated by the green star. No matter what, something can generate phonons. Phonons can then travel through the substrate and reach Cooper pairs in the circuit. If the energy is high enough, they can break Cooper pairs in the circuit and create quasiparticles. The quasiparticles can then recombine and emit a phonon of the same energy. This phonon can again travel through the substrate and break a Cooper pair in the trap, again creating quasiparticles. However, here, the quasiparticles will need to lose the excess energy before recombining. When they do recombine, the emitted phonon will be able to travel through the substrate, and it will also be able to reach the circuit again, but it will now lack the necessary energy to break Cooper pairs in the circuit. I can make my circuit with granular aluminum and my trap with aluminum, as I mentioned before. And as I mentioned before, we can make several circuits by sweeping the gap of granular aluminum by making it with a different resistivity. It will follow the dome shape that I've shown before. And if we then look at the noise spectral density of the resonators, we will see that the noise is anti-correlated with the superconducting gap of granular aluminum. Or better yet, it is anti-correlated with the difference between the gap of granular aluminum, which is the circuit, and the gap of aluminum, which is the trap. This first hint at the effectiveness of phonon traps that we highlight in this publication prompted us to follow through and make another test of phonon traps that we implemented. Yes?
Francesco, how do you measure F circuit over 2?
We do it with two ways. We can extract the critical temperature, or we can directly measure the gap from terahertz absorption.
Do you have that ability to do that direct measurement with terahertz?
We do this with Martin Paplet interferometer.
Mm.
This is detailed. This technique is detailed, if I may go back some slides, from this article that I show in the bottom.
Thank you.
What I show here is an implementation of phonon traps with the circuit that I've illustrated before. Again, our 3 granular aluminum strip lines sitting on a sapphire substrate and surrounded by lower gap aluminum. We pattern the lower gap aluminum, the trap, as a lattice, square lattice of square aluminum islands. 10 micrometer inside. And we fabricate 4 different samples by sweeping the pitch, the lattice constant of this structure, obtaining different packings, different coverage of phonon traps on our substrate upper face. And we measure and we fabricate a control chip without phonon traps to test, to assess the strength of phonon trapping.
Francesco, yeah, that's very interesting. How do you choose the size for your initial approach? Why not have one big one? Why have, why 10 microns, not 100 microns versus 1 micron?
This was a small enough feature size that allowed any resonant phenomena of the islands to stay well outside our band and to ensure no flux trapping in our lower gap material, while being easy to fabricate with our technology. What I show here is the time evolution of the resonant frequency of resonator A for our control sample without phonon traps. We see that we observe the quasiparticle bursts that I mentioned before. And if I zoom into one of them with the gray square, we can appreciate their relaxation time of the order of 1 second. What happens if we had phonon traps? This is the same setup with 19% coverage, 19% filling factor of phonon traps. We can appreciate that the baseline of the fluctuations of the resonant frequency gets quieter. We observe less quasi-particle bursts, all the while maintaining the same relaxation dynamics for the quasi-particles.
Francesco, this is very nice. Does that mean that if a chip has a ground plane everywhere, right? So the chips you have don't have a ground plane, but if you had a planar chip, not a 3D chip, with a ground plane, sapphire or silicon, you would expect that ground plane to act as a phonon trap?
Yes, and later on, I will show how we extrapolate how better this could get for a higher coverage of lower gap metallization.
And is it important that you have the grid, or what if it's a continuous single galvanic connection, big island?
That could also work. It's not necessary to have a grid structure like this.
Mm-hmm.
What could also be interesting is once one is able to get a much smaller feature size to create a phonon crystal with those squares, which will not allow phonons to travel through it and to reach the resonators. This would be an additional beneficial effect. But for this, one needs much smaller features, and we didn't have the technology to explore that yet.
Yeah, you mean a band stop. We have a question here from the folks. Did you also try the phonon traps for qubits to see whether they can improve the qubit T1s as well?
It's one of our next projects. It's coming up.
Okay, we'll stay tuned.
Yes, please do.
Oh, and the second part of that question was, is there a difference between sapphire and silicon? How would those two materials differ, or are the results going to be more or less the same?
We only tested on sapphire, so any comment I could make would be pure speculation. We didn't test on silicon, I'm sorry. We only tested on sapphire.
Mm-hmm. Thank you.
What I show in this slide, in this graph, is the burst rate. How many quasi-particle bursts do we observe over time as a function of the phonon trap coverage, the phonon trap filling factor for our three resonators A, B, and C. And we can appreciate that this rate is decreased monotonically for all our resonator types. The solid lines represent fits to a phonon trapping model that we developed in this publication, which allows us to extrapolate how well it would get for a full coverage of phonon traps or something that gets close to it. And in principle, this would lead up to a 5-fold reduction in the quasi-particle bursts. I think it's also interesting to note that the case for no phonon traps gives a burst rate that is comparable to the one observed by other groups with similar substrate size, as I report with the 3 markers, red markers. And as I mentioned, another probe for quasi-particle induced degradation in our samples is the internal quality factor that I show here, again as a function of the phonon trap filling factor. We can appreciate that for resonators A and B, the improvement is still monotonical, while the picture is more complicated for resonator C. It means that at least some of resonators of type C have a dissipation that is limited by something that is not quasiparticles generated by phonons. Again, we can fit this data to our model and extrapolate what would happen for a full or almost full phonon trap coverage. And these would yield a tenfold increase in internal quality factor at single photon drive. The other approach that we can have is reduce the radiation that generates the phonons in the first place. And we can divide this radiation into two components: a local radiation coming from impurities in our cryostats, and environmental radiation, such as cosmic rays. And there's two ways that we can counteract them. To get rid of local radiation, we can clean our setup, which I show here with the artistic depiction of our waveguide being dipped into acid. And we can get rid of environmental radiation by shielding our cryostat, surrounding it with a lead shield, and by shielding it with a mountain, meaning that we achieve that by measuring in the Laboratori Nazionali del Gran Sasso in Italy, where a 1.4 kilometer rock overburden provides shielding.
And Francesco, we have two questions here. What benefit might phonon traps on the backside of the chip have?
They could definitely also have a beneficial effect. We didn't try that, but this should be tried.
And is there a characteristic size for the phonon traps where below that size it just wouldn't work anymore?
This is an interesting question, but I think, imagine this. Imagine we just have a thin wire of trapping material, meaning a thin wire of aluminum enclosing our circuits. Thin, not thick, thickness-wise, but width-wise, not very wide. This would still have a beneficial effect because phonons would have to pass through there, and they would have to break Cooper pairs there. And the less wide you make it, the less efficient it would be, but it would still have an effect.
And I guess what we're talking about right now are surface phonons, right? Because you have bulk phonons, which can come in any angle to the plane and have some scattering section. And then you also have the surface phonons.
Yes. Is there a follow-up?
Oh, I guess when you say that surrounding the qubit with a guard like that, right? Or maybe a phonon stop band crystal, that would only help for surface phonons, right? Not bulk phonons that could couple from below. But those, I suppose, would have maybe a lesser coupling, right, to the structure.
You are right. With those, they would not be affected by our traps are on the surface, so we would not have an effect on phonons that reach our circuit from the bulk.
Nice. And is the thought right now to operate under that most of the phonons we should worry about are the surface phonons and less of the bulk phonons?
I cannot comment on that. I would say that our outlook is more like a part of our phonons will be on the surface, and this is a step that we can take towards solving this issue.
So if I may add, I don't think we've done any experiment to differentiate between surface and bulk phonons. So I think what we see here is the combined effect, and I think one parameter that should improve, if we want to make this absorption better, one parameter that will improve the absorption. Correct me, Laura, if I'm wrong, right? I mean, you are the expert. But from what I understood talking to you guys, the thickness of the phonon traps is quite important. So if we could make those traps thicker, I think we would win. Is that correct, Laura?
Yeah, at least in the first place, the probability that you absorb in the end of phonon is proportional to the volume of these traps. So you're right. I think so.
And how would you reply to the question about the size of the phonon traps? Is there some size? I guess something related to the length, to the wavelength.
Could you speak a little louder, Johan? It's a little quiet.
Oh, sorry. No, I was just asking Laura what she thinks, how she would reply to the question you asked about the size of the phonon traps.
I don't have an answer supported by numbers. So we made some attempts, but in the other direction. So we wanted to trap the phonons to increase our signal in the superconductor. So the opposite direction is something we should explore more in depth.
Good, thank you. Yeah, because I know that it's, I mean, from some studies I've seen, I happen to be familiar with like Yuan Chu's work, coupling bulk phonons to transmon qubits. They had to work very hard actually to couple them very strongly. So I suppose it's, that might be a good thing for the questions here. But anyway, we can proceed.
Yeah, but indeed, our phonon coupling efficiency is very small actually. It's like some 0.00, some fraction of a percent.
Yeah, that's something that I think it was in one of the questions before, how we were so sensitive to phonons, and actually I wouldn't say we are so sensitive to phonons. Because I mean, people that do this kind of devices for NKIDs or other kind of particle detectors, they have an efficiency which is at least 2 orders of magnitude higher compared to the efficiency for phonon absorption that we have with these kinetic inductance detectors. So maybe this was also related to your comment about the Josephson junction. There is for sure an effect of the surface. So the larger the surface, the more phonons of the inductance, the more phonons will turn into signal in your device. But this is hard to extract over so many orders of magnitude of size. So we work with something of the order of millimeter square, which is not the order of magnitude of the Josephson junction surface. So this is why I mean it's difficult to extract over many orders of magnitude. We need some measurements to extract some parameters.
Yeah. So my intuition about these quasi-particle bursts is that even a single ionizing event in the substrate leaves behind so many phonons, right? You have a deposit of up to 1 MeV. You leave behind so many phonons that even though you have a relatively poor phonon absorption in your circuit, you still absorb a lot of them because there are a lot of them to begin with, and that's why we still care about them.
Yeah, for sure. When we have our, in our detectors, we measure something of the order of keV or even less, and it still produces signals in all the circuits that are deposited on a 2 per 2 centimeter square substrate. So you're right, even a small amount of energy produces so many phonons, and they travel all around that in the end the signal is all of them. But, sorry for the interruption.
No, thank you for answering that. It's a very good question, and we're coming up on the hour, but there's no hard stop for us. So folks the video will stay up, so we can let Francesco resume.
I will just quickly go over once again this slide, which just says that there's two approaches that we can have to reduce the impact of radiation: cleaning to reduce the impact of local radiation, and shielding, which will reduce the impact of environmental radiation. To test this, we made measurement in 3 setups. The first setup is the cryostat in Karlsruhe Institute of Technology, which is our control setup, meaning it was not cleaned and not shielded. As we can see, our granular aluminum resonators are sitting on the Sapphire chip, which we glue to the waveguide either with silver paste or vacuum grease, depending on the setup. In this one, we used silver paste. And the waveguide is then surrounded by a copper aluminum sandwich and a mu metal barrel inside the mixing chamber. This is a magnetic shielding. Then we have a setup where we cleaned to get rid of local radiation. And as we can see, our copper that I show now with a different color was cleaned with acid etching. We performed 2 runs in this setup, one with silver paste and one with vacuum grease. And finally, this is our setup with both strategies applied, cleaned and shielded. The clean waveguide was brought in the cryostat under the Gran Sasso mountain, and the cryostat there was surrounded again by a mu metal magnetic shield and by a wall of lead bricks. What is then the effect on our metrics, on the number of quasi-particle bursts and internal quality factor? I will show first for one resonator, since it's comparable for all resonators, the effect on the quasi-particle bursts. Starting from our control setup in Karlsruhe, or K, in which we measure a rate, quasi-particle burst rate of about 80 millihertz. Order of magnitude is 1 every 10 seconds. Then chronologically, the next measurement is in the best setup, that is the Gran Sasso setup, where it's clean and shielded. And we see a marked reduction in quasi-particle burst rate by a factor 50. As a control, in this same setup, we can first remove the lead bricks surrounding the cryostat, shown by the circle, which will increase the burst rate. And we can add a thorium source, radioactive source, close to the cryostat, which will then bring the burst rate to values that are above the ones measured in the unclean and unshielded setup, which really convinces us that these bursts are radioactivity related. When we measure, finally, in the clean setup, we see that there is an improvement with respect to the uncleaned, but we also see that shielding in the mountain plays a great role in reducing the burst rate. And we can appreciate that using vacuum grease instead of silver paste, vacuum grease being more radio pure, has also a small but visible beneficial effect. And for the same resonator, this is the effect on the dissipation of the internal quality factor. We see that by cleaning and shielding, we again see a beneficial effect. We see a reduction when we add the thorium oxide source, while when we measure in the clean setup, it's not clear why we get a lower value with respect to the control setup. However, if we look at all the resonators, we see that what is consistent is cleaning and shielding always improves the amount of bursts that we observe. It reduces it by up to a factor of 50, and it always increases the internal quality factor up to a factor of 4. Which brings me to my conclusions. What I've shown in this talk is how we used granular aluminum superconducting circuits to probe quasiparticles, and we were interested in radiation-generated quasiparticles. We can reduce the quasiparticle density by employing phonon trapping to get rid of the phonons generated in the substrate. And as a complementary approach, we can reduce the quasiparticle density also by shielding from radiation that would generate those phonons in the first place. The point of the work, the recent work of Vepselainen and co-workers from MIT was to show that radioactivity is deleterious to superconducting circuit and will soon be an issue for transmon type qubits, while it already is in other type of qubits. And what we hope to show with this work is that this is not a bleak scenarios. We have tools to fight the negative effects of radiation in superconducting quantum circuits. Thank you all for your attention.
Thank you, Francesco, for the great talk. And yes, I think you can probably, there we go, stop sharing the screen. Also, thank you, Laura and Johan, for joining us today. I'll let us have a minute here to see if there are any final questions that we might have about the talk. We did have a lot of questions during the talk. So thank you for bearing with all of those. Yes, I see Hani is sending her thanks for the great talk. And oh yes, well, I see a lot of praises. I don't see any questions yet.
Good.
I hope this was interesting for you.
Watching, oh, thanks,
oh, Kyle. Oh, Kyle. Hey, Kyle. Great you're watching too. And Amir. Amir's here too. So I'm glad we could get the community together today for this. You know, thank you everyone for joining us. Seeing no further question, I'll just give us a minute to see if you have any final words or comments.
I am very glad of receiving so many questions that I'll take it as a sign that people like this. So thank you.
I know I enjoyed it thoroughly. We've been thrilled to have you on the Quantum Seminar this Friday. Please, you know, subscribe to the YouTube channel if you want to receive more seminars like this. We'll be doing this every Friday. And oh, we do have a question, actually. Sorry, I just saw it. What would be the next directions for you? What are you thinking about following up or pursuing next?
Yes, the missing link is to show that the improvement that we have shown on resonators is translatable into improvement in qubits. For instance, checking that phonon traps will improve the T1 of a quasiparticle dominated qubit such as a fluxonium qubit, or that going underground or shielding very properly the cryostat and cleaning from local radioactivity would improve the coherence. This would be the next step.
So would you recommend for, oh, I see Johan, go on.
Yeah, no, I wanted to say that, of course, qubits are the next step, but we don't expect actually big surprises because these resonators are quite a tool to mimic what we will see also in qubits. I think a more fundamental question is to understand the chain of phenomena, you know, that take one MeV of deposited energy in the substrate and convert it into problems for the qubit community, right? So I think it's not clear how long is the list of these problems. It's not clear what exactly are these problems. There could be charges created, right? You could have phonons that activate not only quasiparticles, but also some defects in your dielectric. And so there might be much more than just quasiparticles coming out of these impacts, because again, the energy is 6 orders of magnitude above the characteristic energy of our device.
Right, and I mean, as you also introduce traps, for instance, right? If you have a huge ground plane, which looks really nice because it's a phonon trap, but then it's also great for having vortices trapped there. So now you have, you know, competing effects as well. So it will be very interesting to see.
Yeah, and it's not obvious because you need a ground plane that's lower gap than your devices, right? I mean, an aluminum ground plane for aluminum devices doesn't work that great. Okay, for niobium, I guess it would be better, but the electrodes are still aluminum.
So what does that mean if your ground plane is niobium, but your junctions are aluminum? Does that mean your junctions are a quasi-particle trap?
I mean, I think so.
Good. Well, it sounds like there's a lot more discussion, and I'm sure we'll have a follow-up to keep an eye on. So thank you, Laura, Johan, and Francesco for tuning in. And thank you also for everyone watching for tuning in as well, and for all of the great questions. And join us next Friday. So with that, I'd like to wrap it up and thank the speakers again and thank the audience, and we'll see you next week.
Thank you.
Bye-bye.